morning, I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next part of Unit 4. So, in the previous lecture we have discussed about pulse code modulation. So, in this case it is we have talked about regenerative circuits, which is the part of transmission path. So, this is the block diagram of the regenerative repeater. So, at the input of the regenerative repeater there is a distorted PCM. Why distorted PCM? Because it will be affected with noise, which will going to degrade the quality of the signal at the channel. So, here we are having the distorted PCM. This will look like somewhat this one. So, you can see that this is affected with noise, the amplitude is affected with the noise. So, the main aim of this regeneration is to remove this noise, and we have to reconstruct the PCM signal like this one. So, the first block of this regeneration is the amplifier or the equalizer. This is amplifier. Equalizer. Now, equalizer, the main aim of equalizer is to equalize the effect of noise, is to equalize the amplitude. Now, this is passed through a timing circuit. Now, timing circuit, the input is given to this decision making noise. So, what is decision making noise? It is like when we have to set up a threshold value. When the amplitude, this one, crosses that threshold value, then we can say that 1 is present, 1 is there at the input, and when this threshold is not there, then we can say that 0 is there at the input of this decision device. So, that is how we can reconstruct this regenerated PCM wave. Next one is a regenerative repeater consists of an equalizer, a timing circuit, and a decision making device. So, these are the three main building blocks of a regenerative repeater. The equalizer is used to undo the effect of the transmission channel to get back the pulses in their original shape before the transmission. So, the amplitude and phase distortions caused by some characteristics of channel is removed, and the shape of the pulses. So, basically equalizer will going to remove the effect of noise from the amplitude and phase distortion. Next is timing circuit. Now, it is used to recover the clock of the transmitted symbol, thus providing a periodic pulse train. So, that is the work of this regeneration. A decision making device is used to detect the different pulses based on threshold information. Each sample is compared with the threshold value. So, if it exceeds the threshold value, then we can say 1 is present, and if does not exceeds the threshold, we can say that 0 is transmitted. The generated signal differs from original signal due to the following errors. So, these are the two main causes that why the error has occurred. First one is due to the presence of channel noise and interference. Wrong decision are made and bit errors are introduced in the regenerated signal. And if the spacing between the receipt pulses is deviates from a signed value, a jitter is introduced in the reconstructed signal. So, that is the case that why the noise is been present. Now, next is channel noise and error probability. So, channel noise basically introduces a bit error into the received signal. Let us say 1 is present and we have detected by mistaken that 0 is there. So, that is the case of bit error. So, the and there is also a term that is used to be calculated, that is bit error rate. Like 10 bits have been transmitted and 2 bits are having an error. So, the output of this bit error rate will be 2 upon 10. Next is, if the bit error is more, the received output becomes dissimilar compared to the original message signal. So, 10 bits are transmitted and let us say 5 bits are having an error. So, the information that we have reconstructed from these 10 bits or the output, that does not make any sense, because 50% of the bits are having error. Next one is the fidelity of transmission by PCM is the presence of channel noise can be measured in terms of error rate of probability of error, which is defined as the probability that the symbol at the receiver output differs from that which is present at the transmitted one. Next one is the quantization error. So, this is the case of quantization error, like you can see that the sampling time is shown by 0 Ts, 2 Ts, 3 Ts and so on, then there will be 4 Ts, 5 Ts. So, that is nothing, these are the sampling times. So, and we have used V is equals to 3, V is equals to 3 means the encoder size is equals to 3. So, you can see that 8 different options are available from 000 to 111. So, this is how we have used the encoder which will going to produce this particular type of output. So, this is the discrete samples that are quantized, this is quantization error. This one is the analog signal which is reconstructed from the samples that we have collected from the sampler. Next one is resolution and quantization error. So, more number of bits used to represent every sample leads to better resolution and less quantization error, which means that if somehow we can collect larger number of samples from the input signal, then it will going to ease our work and it will reduce the noise that has been generated. So, the received signal will be very close to the transmitted signal. This is what we have learnt up from the error. Next is this diagram is basically showing that when we have considered 2 bits of encoder like 00 to 11. So, 4 options are there. So, that only depends upon the dynamic range of the input signal. Now, when we have considered 3 bits of information like 000 to 111. So, this is how the dynamic range will be uh, divided, and this is how we can generate a staircase approximation of the signal. Now, next we have considered this V is equals to 4. So, 4 bits is are considered to represent this dynamic range of amplitude like from 40 to 41. So, this is how we can design the encoder. Now, this is the basically showing the staircase approximation, and we can easily construct the original signal. Now, this red line shows the original message signal which can be approximated from the staircase approximation. Now, next we will consider a very important parameter that is signal to noise ratio. Now, by calculating this signal to noise ratio, we can at the input of the receiver, at the output of the receiver, we can calculate SNR, and after calculating this SNR, a very important parameter that we can figure out, that is figure of merit, FOM. A figure of merit, the inverse of this FOM is noise figure. So, these two important parameters that will going to decide that whether the receiver is working correctly or not, whether whatever we have received at the receiver input is reconstructed at the receiver output. So, that is the case of SNR. So, consider a memoryless quantizer. Each sample is quantized independently, that is both uniform and symmetric, which means that delta is constant and it is symmetric across the origin. So, this is how you can see that this is delta, this is constant and it is symmetric about the origin line. So, that is the transfer characteristics of the quantizer. So, it is divided into L L number of levels. So, you can see that these are the number of levels. So, that is L. Let X denotes the quantizer input and Y denotes the output. So, the equation will be somewhat like this one, and L is the number of levels is equals to 2 into X max divided by delta. What is X max? X max is the maximum amplitude of the signal. Let us say in this case it will be 5 volt, it will vary from -5 to 5. So, 5 volt will be the X max value multiplied by 2 divided by delta. Now, delta is nothing, this is the step size and it will be constant in this case, that is because we have considered the uniform quantization. Now, next you can see that how these values can be represented. So, these are the quantization level. Now, you can see that this is from minus Vp to plus Vp, means peak to peak voltage, that is Vpp. Vpp is nothing, it is peak to peak voltage and it is divided into L number of levels from minus Vp to plus Vp. So, that is the quantization level. Now, next is the quantization noise and signal to noise ratio. So, this is decision threshold of the quantizer, like this is xk minus 1 to xk plus 1, it will going to vary, and this will be the center value, and that will be having the noise. Let us say my value lies over here and I have rounded off to this one. So, this much will be the quantization error, means sampled value minus the subtracted by the original value. So, that will constitutes the quantization error. Now, next comes the quantization noise and signal to noise ratio. Suppose that the input x lies in the interval from xk to xk plus 1. So, k will vary from 1 to L, where L is the number of levels. So, correspondingly the quantizer output y takes on a discrete value. So, that is denoted by y is equals to yk. So, let q is the quantization error with values in the range. Now, value range will be from minus delta by 2 to plus delta by 2, then this will be yk will be is equals to x plus q. Now, x is the input signal and q is the quantization error. So, this is the diagram, the graph which is showing the peak to peak value excursion from minus 7 delta by 2 to plus 7 delta by 2, and this will vary from minus 3 delta to plus 3 delta, and these are the input images. So, this is how we can generate a waveform, that is quantization error. Now, next is quantization noise and signal to noise ratio. So, quantization noise is uniformly distributed throughout the signal band, and its interfering effect on a signal is similar to that of the thermal noise. So, the PDF of this quantization error is denoted for minus delta by 2 to plus delta by 2, its value will be 1 upon delta. So, this is how we can make this. Minus delta by 2 to plus delta by 2, its value will be delta 1 upon delta, sorry. So, its amplitude. So, that will be the PDF of this quantization error that can be plotted in this way, and otherwise its amplitude will be 0. So, from here we can calculate its mean and variance, that will going to give the power of the noise signal. So, this is how the variance will be calculated from minus infinity to infinity q square f q q d q, and sigma square, that is variance that we can calculate is expected value of q square. A variance formula is expected value of x square minus expected value of x ka whole square. So, this will be the mean of quantization error is 0 and the variance is same as that mean square value. So, this will be the formula that we have seen over here. So, this is the representation. It can also be represented for and not by 2. For f x is from 1 upon b minus a, x will vary from a to b and 0 otherwise. Now, this is the formula that how quantization noise, that is this will be equivalent to n q quantization noise delta square upon 12, and since we have to calculate the signal to noise ratio. So, that will be signal power upon noise power. So, sigma x square upon delta square by 12. Now, the smaller we make the step size, the larger will be the signal to noise ratio. So, which means it is inversely proportional, that will be shown by this diagram only. Now, again we can calculate this value. So, after putting the value of L and x max, it will be x max divided by 2 to the power n minus 1 minus whole 1. So, that will be the step size. Now, signal to quantization noise ratio delta will be equivalent to 4 sigma x divided by 2 to the power n minus 1 minus 1. So, signal to noise ratio at the output is equals to 3 upon 16 2 to the power 2 n. Now, there are two formulas that are associated with signal to noise ratio. SNR is generally described in terms of decibel only. So, when we are considering the amplitude normalized amplitude, then its value will be 1.76 minus plus 6 n, and when we have considered the normalized amplitude, then it will be normalized message signal, then that will be 4.82 plus 6.02 V. So, that are the two formulas for signal to noise ratio. This is the derivation that is related to SNR, where we have first calculated the power of the message signal, then we can put over here, and this is the value. You have to convert this value into decibel, taking the log of this value and multiply it by 10. This is signal to noise ratio. This is the formula 1.8 plus 6 R. So, this is all about today's lecture. Thank you.